All right, welcome. This is a special video from my honors statistics classes as we go over chi-square test for independence. All right, so we're going to do a chi-square test of independence using a p-value, not using the rejection region that your textbooks promotes, and that's so that we can use a calculator to do the test, and it's also more clear. All right, let's start by looking at a problem. So we have a health club manager that wants to determine whether the number of exercise hours per week is related to gender. Okay, so we're trying to compare the variables of gender, male and female, with how many days per week that they exercise. As with all chi-square independence tests, we're getting our data from a random sample. In this case, with a sample size of 275 students, and we're going to set our alpha, our significance level, at 5% before we begin our test. Okay, and we want to know, is there enough evidence to conclude that the number of days that a student exercises is related to whether they're a male or a female. Okay. So the first thing we want to do is determine our degrees of freedom. And rather than using that little formula the book gives, I like to take my chart, cross out one of the rows and one of the columns. Notice I don't include the totals. What's left? What's left are just 3 cells. And that's my degrees of freedom, 3. Another way to look at it is we have a 2x4 table. So subtract 1 from 2, subtract 1 from 4, and we have a 1/3 degrees of freedom. Okay, 3 degrees of freedom. All right, we're going to start, as we always do with any test, with a null hypothesis and an alternative hypothesis. In this case, as always is going to be with this type of test, the null hypothesis is going to be that the variables are independent of each other, or in this case, that the numbers of days of exercise per week is independent of gender. Our alternative is going to be that they are not independent, or to put that in a more positive way, that the number of days of exercise per week depends on gender. All right? So we've already determined that we have a significance level of 5%. We've already determined our degrees of freedom are 3. And then we're going to do a chi-square test. So we're going to use this formula here, where sigma means we're going to add up all of these contributions, which we're going to find by the observed value minus the expected count, all squared, all over the expected count. So we'll go through that. Okay, note, all expected counts must be greater than or equal to 5 to do this test. And so the first thing we're going to do is calculate, find out how we get those expected counts and make sure they're all greater than 5. All right, so each count in our table is our observed count. In other words, we got those counts from our random sample. So in this case, what does the 40 represent? There are 40 males that exercise between 0 and 1 day per week out of our 275 total people, or our 125 total males. To calculate the expected count, we want to take, just remember this simple formula. We take total times total divided by grand total. Okay, order doesn't really matter here. So we're going to take the total number of males times the total number of those that exercise 0 to 1 days per week, and we're going to divide that by our sample size, our grand total, 275. And I've done that right here, and we get an expected count of 33.6. What does that mean? 33.6 means that if gender and exercise per week are not dependent on each other, if they are independent, then we would expect from a sample of 275 people to get 33.6 males that exercise 0 to 1 days per week. Now, notice it's a decimal. That's perfectly fine. In fact, in this case, I've rounded it to the nearest tenth, which is okay for your work. And we'll see later that rounding does have a cost, but since there's a lot of math involved, we're going to round to keep it simple. Okay, so, but do round it to the tenth place. Keep that decimal, that's important. All right, so again, column total times row total divided by grand total gives us our expected count. Let's do one more. Okay, so there are 34 females that exercise between 0 and 1 days a week. And so if we take the 150 females times the 74 people that exercise 0 to 1 day per week, divided by the sample size of 275, we get approximately 40.4. So 40.4 is our expected count for that cell. Okay, if you want to pause the video and do the rest yourself, that would be good practice. I'm going to go ahead and show you all of our expected counts. All right, so I've gone ahead and calculated them to the nearest tenth. Okay, so let's go back to that condition we need to satisfy before we can do this test, and that is that all of those expected counts must be at least 5. All right, and we can see that the lowest expected count is 7.7. Therefore, we can continue with the test. We have met that condition. All right. Another thing, you can look already, and the closer the expected is to the observed, the smaller the chi-square we're going to get, and the less likely we are going to be to reject our null hypothesis. So just something to think about. All right, let's move on. So for each cell of our table, we will get a contribution. And when we add all of those contributions together, we will get our chi-square number. The higher the chi-square number, the bigger the contributions, the more likely we're going to get a lower p-value, and the more likely we are to reject the null hypothesis. All right, so because you have to worry about order of operations, I've shown this in 3 steps, right? So to find the contribution for this first cell, we're going to do 40 minus 33.6, which is about 6.4. And if we square that, it's about 41. And then we divide that again by our expected count, which is 33.6. We get approximately 1.2. Again, I've rounded to the tenths, and that's fine for this, for doing this by hand. All right, so take a moment and look and understand that how I followed the formula to get that value of 1.2. In each cell, I have the contribution. Hopefully, if you did the calculations yourself, you got the same thing. Of course, if you didn't round, you'd get a little more accurate values for this, but for the purposes of this activity, these are fine. Okay, so we're ready to go ahead and calculate the chi-square value. The chi-square value is simply the sum of those 8 different contributions. And in this case, that is 3.8. Okay, what does 3.8 mean? 3.8 is the value in our chi-square distribution that we're going to calculate our p-value from. Okay, so I've given you the steps on your TI-84 here, and so I'm going to kind of do it, but you're going to want to do this on your own. So on the TI-84, I'm going to go to the distribution menu. Don't forget to press the second button first. You're going to see the list of distributions there. And I'm going to select number 8, which is the chi-square CDF. And for my lower value, I put in our chi-square, which is 3.8. Remember, this is always a right tail distribution. So our lower value is always going to be the chi-square value, and the upper value is always going to be, 999, however many nines you feel comfortable with. The more the merrier. Okay, don't forget to put in the degrees of freedom, which we know to be 3, and then simply press paste and enter. Okay, and if you do that, hopefully you got a p-value of approximately 0.284. At the beginning, we set our alpha, our significance level at 5%, meaning we are only going to reject our null hypothesis if our p-value is less than 5%, 0.05. Clearly, it is not. So let's develop a conclusion on this. So because 0.284 is greater than 0.05, we fail to reject our null hypothesis that the number of days of exercise per week is independent of gender. Now, what does that mean? Does that mean that it is, if we fail to reject it, does that mean it is independent? No. Remember, we never accept our null hypothesis. All it means is that we don't have enough evidence to show that the number of days depends on gender. I'm going to show you a couple other options for calculating your p-value and a cheat if you stay till the end of the video. All right, so first of all, I have a nice online calculator here if you don't have TI-84, and this will calculate your CDF for you. Let me go to the online calculator. Here we go, and notice if you go to that page, it's just going to ask you for your chi-square value and your degrees of freedom. I've already put them in here, and calculate, and then you see that it will give you your p-value right here. What's really nice, it'll give you this graph too. And then the last thing I wanted to show you was the cheat. It's not really a cheat. Think of it more as a calculator check. So what we can do on the calculator, without rounding off to get our actual p-value and such, we're going to go to our matrix button. This is because the information comes in a table, the calculator handles it in a matrix. So don't forget, press the second button before the matrix button, which is right below the math button. All right, and then you go over to the edit menu and select matrix A, or just number 1. You need to set your matrix to the correct size. Original table is a 2 by 4. So you want to put 2 by 4 in the matrix, and then you want to enter the numbers in going left to right, top to bottom, just like you read. So 40, 53, 26, 6, 34, 68, 37, and 11. Quit. So second, quit, and then you're going to select the stat button. All right, remember the stat button is the one we use for all tests. So after I press stat, go over to the tests menu and go down to the chi-square test. Not chi-square GOF, but the chi-square test. Should be C on most calculators. And then your observed and expected should already have matrix A and matrix B in there. Just leave that alone. You don't have to put anything in for matrix B. The calculator does that automatically. That's your contributions. All right, and then you go to either calculator or draw. You can say, wow, because look at that. It's going to give us our p-value, and it's going to give us a beautiful curve. All right, so p-value comes out to 0.3216, a little different than we got calculated by hand. Why? Because of rounding error. Okay, so, but this is a good check after you've done your work. Hint, if you check matrix B, you're going to discover another secret. All right, guys, I hope this was helpful. If you have any questions, you can definitely email me or comment below on this video.